Looking for runts and glitches in a digital signal is one of the most common debug tasks design engineers face today. In this video, we'll look at the abilities of three mid-range oscilloscopes to debug a series of digital signals from LaCroix, Agilent, and Tektronix. The objective is simple: to discover the signal, capture events of interest, search for recurring events, and analyze the end results. To accomplish this, let's perform 4 tasks on each scope. 1. Monitor the signal to discover if runts and glitches exist. 2. Capture the runt. 3. Search for all occurrences of a setup and hold violation to determine how frequently it occurs. And 4. Analyze jitter issues on a fast signal with built-in tools. Let's find out how each scope performs in addressing these tasks. The first test task is to discover any runts that may exist in a digital signal. This task is using a 622 megabit per second digital signal with a runt programmed into the data channel. Its occurrence is very infrequent, making identification a difficult task. Here we see how quickly the Tektronix DPO7000 finds the runt pulse on the signal. With the DPO7000's built-in DPX technology providing an industry-best waveform capture rate, you can see just how quickly and easily we're able to accomplish this task. There's enough evidence here to justify that something is going on, requiring more debugging. What if your scope doesn't have a fast waveform capture rate? Let's look at the Agilent MSO9000 to see what happens. First, we'll turn on color grading and increase waveform intensity. Now let's see if that helps us find the runt. Notice that the very common signal pulses are obvious, but after watching for a while, it's evident that the Agilent instrument cannot see the runt signal between the common pulses. Now let's see what we get with the LaCroix WaveRunner. The WaveRunner has some similar capabilities as Tektronix, but it also has a significantly slower waveform capture rate and is unable to see the runt signal between the common pulses. With the lower waveform capture rates on the Agilent and LaCroix scopes, the question remains open: should we continue with debugging, or is the signal okay? After performing test task number 1 to discover the signal, finding a runt pulse is done much faster with the Tektronix DPO7000 than with competing instruments. Next, let's try to capture an important event of interest. Here we see how quickly the Tektronix DPO7000 does just that. With its pinpoint triggering capability, we can capture the runt and evaluate the transition time associated with the clock signal in a couple of simple setups using the A/B trigger functionality of pinpoint triggering. What if your scope doesn't have a comprehensive set of A/B event triggers? We can see on the Agilent MSO9000 what happens. Because the MSO9000 is missing the B event triggers commonly used for a transition time violation tied to evidence of a runt on the data signal, it can't properly capture the event. Instead, with the Agilent instrument, you have to capture the runt and manually search for clock transition time anomalies. Here we use a basic trigger to capture the runt. We then must manually scroll through the waveform looking for a specific transition time error. We could also try to trigger on the transition time error with the hope of discovering the runt on the data channel, but that still takes up valuable time. Now let's try the LaCroix WaveRunner. Here we've captured the clock signal with a standard edge trigger, but we're having a difficult time looking for a transition timeout trigger for the B event in its trigger system. It looks like we can do a qualified A/B trigger, but the B event is only allowing us to select an edge trigger. How do we know this captures the event accurately? How do we know we have the proper trigger settings? The LaCroix trigger system leaves many questions unanswered. After performing test task number 2 to capture an important event, it's easy to conclude that the Tektronix DPO7000 has the best trigger system for capturing complex signal anomalies. Next, we want to search for those obscure instances of a setup and hold violation on a captured clock and data signal. Here we see how quickly the Tektronix DPO7000 does just that. With the DPO7000's advanced search and mark feature, you can easily set up and automatically search the waveform looking for a specific setup and hold violation of 2 nanoseconds. First, we'll turn on the DPX display to see what's going on with the signal. Then we'll set up a search to look specifically for a setup and hold violation on the clock and data signal pair. The scope can now directly go find that obscure instance in the record. Once we have it, we can use the zoom functionality to look for the setup and hold violation to see exactly what's causing it. Now let's search again for the next instance. See how easy it is to tab ahead and find it? What if your scope doesn't have automated search for setup and hold violations? We can see on the Agilent MSO 9000 what happens. Because the MSO 9000 doesn't seem to have automated search for common signal anomalies like setup and hold violations, you must tediously search your entire waveform manually with different limit test criteria to see if there is a setup and hold violation. Even then, the Agilent MSO 9000 has not found the runts in the digital signal. After performing test task number 3 to search for specific events of interest, searching for and finding specific setup and hold violations is easiest and fastest with the Tektronix DPO 7000. For our final task, let's perform a jitter measurement to analyze that 622 megabit per second signal to identify potential timing errors. With the Tektronix DPO 7000, we can quickly perform jitter analysis using DPO-Jet's one-touch jitter. With a simple menu selection, we can get a complete 4-plot view of the eye pattern, histogram, frequency plots, and bathtub curve of the 622 megabit per second signal. We can also dig even deeper if we want, using the additional measurement analysis data shown here. With the Tektronix one-touch jitter capability, performing complex timing analysis is easier and faster than ever. Now let's see how the Agilent MSO 9000 handles jitter analysis. The Agilent MSO 9000 has a feature called EasyJit. Let's see how easy easy is. Using the same signal and running the same jitter measurements, we're finding that many more steps are required, which are time-consuming and not so easy after all. When you sum it all up, the comparisons speak for themselves. The Tektronix DPO 7000 oscilloscope accomplishes the objectives better than other mid-range oscilloscopes on the market. The DPO 7000 can discover runts quicker with DPX FastAct technology. The DPO 7000 is better for fast capture of the runt and its complex clock and data relationship using pinpoint triggering, the most advanced trigger system on the market for mid-range scopes. The DPO 7000 is more efficient in a search for hard-to-find yet important events using advanced search and mark. And finally, the Tektronix DPO 7000 can analyze jitter and timing quickly and easily with the award-winning DPO-Jet analysis toolset and one-touch jitter. This scope comparison confirms what oscilloscope users have known for over 60 years. The Tektronix DPO 7000 series oscilloscopes offer a comprehensive set of tools for every stage of debug, so you can quickly discover and capture problems in your design, then search and analyze those problems to find root cause, fast. That must be why 8 out of 10 engineers use Tektronix oscilloscopes on their bench.